Hey Matrix, welcome to the next video in the physics playlist. Today we'll be going over question 6 of the November 2020 physics past paper. If you don't have the paper, then please pause the video now. There's a link in the description where you can go and download the paper and the memo, and once you have the question, then you can continue with the video. Okay, let's get started with question 6. Okay, now question 6 is looking at the Doppler effect. So it says a siren on a train moving at constant speed along a straight horizontal track emits sound with a constant frequency. A detector is placed next to the track recording the frequency of the sound waves. The result is obtained, or the results that are obtained are shown in the graph. Okay, so we have a graph here of frequency against time, and we've got constant frequency, and then it drops, and then we have constant frequency again. Okay. So question 1.1 says state the Doppler effect in words. You can go and look up your definitions for the Doppler effect and write down your definition. But what I first want to do is I just want to do like a quick derivation of the Doppler effect for stationary source. I think it's nicely shown this way, and understanding the question helps a lot. Okay, so we have a moving source to the right. We have an observer that's stationary. Okay, and obviously now the source is emitting sound. But now remember, the source is also moving to the left with to the right, sorry, with the initial velocity. Okay, so what do we know already? We know that the change in distance equals the change in my velocity times time. So any object moving from point A to point B, okay, that's how we can describe the motion. But now remember, your lambda is just the length of the wave, okay? And that can also be described in terms of the velocity and the time it takes. Okay, so let's look at lambda in general. Lambda can then be described as the velocity, okay, times the period that it takes to complete it, okay? Now let's consider for lambda 2. Okay, so lambda 2 is in front. That's when the source is moving and emitting. So if we look at this, okay, this is just to visualize what's happening. This is if the source is stationary and it's emitting sound. Now the source is moving to the right, so it's compressing the sound waves as it emits the sound waves. Okay, so we have compression, which means our lambda is smaller. Okay. So what's happening here is we have our lambda, okay, is going to equal to the change in velocity for the wave. Now what's affecting the wave is the velocity of the source and the velocity of the sound wave. Okay, so we're going to have v minus v source, okay, times that by our period. Okay, so with waves, the time taken is measured in periods. Okay, then we know that the formula for frequency is given as my velocity over my wavelength. Now we can just substitute this into my frequency. So the frequency for the observer, okay, so frequency of observer is then going to be my velocity, okay, over v minus v of the source. Okay, in this case the change in velocity is from my air and from the speed of the source times my period. Okay, but we also know that period is equal to 1 over frequency. Okay, and this will be the frequency of my source because this is the period of my source. So therefore the frequency of my observer is going to be the velocity over v in air. Okay, this is also v in air, minus the velocity of my source times the frequency of my source. Okay, so when we're moving towards the observer, we have a negative at the bottom. Now let's look when it's moving away. So once again, when we're moving away now, what's happening? The car is moving and the sound waves are lagging behind. So they are stretching out, which means my lambda now becomes larger. Okay, so once again, okay, that was for lambda 2. So lambda 1 is now going to be when it moves away. So we're going to have a larger wavelength. So therefore, again, we shall have the v in air plus the change or the velocity of the source, okay, and that's going to be times the period of the source, okay, and then we do the exact same thing over here. We'll have lambda or frequency of observer, okay, is equal to the velocity over the change in lambda. In this case it's v plus vs times the t, okay, and then we have ts equals 1 over fs. So f of observer for moving away is my velocity over v plus vs times my frequency of vs. Okay, and that's how we get the formula for stationary, observer, and a moving object. Okay, but now let's get back to the question. 6.2 says, does the detector record the following frequency, 3148 Hertz, when the train moves towards or away? Now, note that we have a higher frequency. Looking at our picture, we have a smaller wavelength, which indicates higher frequency. So a higher frequency will always be towards. Okay. Now, 6.3 says, calculate the speed of the train taken that the speed of sound in air is 340 meters per second. Okay, so now we're going to use our formula over here. Note we have a stationary observer, so the velocity is going to be 0. Okay, so using the values that were given to us, we can do two equations and solve them simultaneously. Okay, so we don't have the frequency of the source or the frequency of the velocity of the source, because we only have the frequency observed by the detector. Okay, so the first one is going to be 3148 is equal to velocity in air. Okay, then it's moving towards, so it's going to be a minus fs. Okay, and the second one that we can do is then 2073 equals to 340 all over 340 minus vs. Okay, and then my fs is also unknown. Okay, now we can equate these two together by getting fs on its own. So we should get the following, 3148 times the following bracket, okay, all over 340 equals to fs. Okay, and on this side we can do the same, 2073 340 minus, this one should be a plus because we're moving away. My mistake there. Okay, so this should be a plus because it's moving away, so we have a lower frequency. Okay, and then that's all over 340, and that equals to fs. Okay, so now we can equate these two together, which means we'll end up with the following. Okay, so once you've got the following here, okay, note that they both are being divided by 340, so that will cancel out. Okay, now we just need to sort out the algebra. Be careful of the negative here. We take all the VS's to one side, all our numbers to the other side, and if you sort out that algebra, you should get to a value of VS equals to 70 meters per second, -1. Okay, velocity -1. Okay, now the last question says the detector starts recording the frequency of the moving train siren a distance of 350 meters away. Now we need to calculate when does it pass the detector. That's technically what T1 is. T1 is the point at where it passes the detector. Okay, so we've just calculated the velocity of the train. Okay, and we have the distance that it's sitting away. So simple velocity formula over here. We have the velocity is 70 meters per second -1. We have the change in distance, which is 350 meters away. Okay, and we need the time taken. Okay, so we take time across, we bring the 70 over. So delta t equals to 350 divided by 70. Let's see, the zeros cancel out. 35 divided by 7 is going to equal to 5 seconds. Okay, and that's how we go about doing the Doppler effect. Okay, if you found today's video helpful, then please leave a thumbs up on the video. If you have any questions regarding this question, please leave them in the comment section down below, and I'll get back to them as soon as I can. Please go check out the channel. While you're there, consider subscribing to the channel, and thank you for watching.